This is a production of Cornell University.
I will talk about tree selection, and hopefully I will end this presentation within the time. Otherwise, we see what we'll do. I will start to try to explain what I mean with improving or urban resilience when it comes to tree selection, because today the urban habitat, or the last decades or so, the urban green infrastructure have been identified as a very important element in order to create the resilience to both current happenings but also future happenings like climate change, but also new functions. We're giving more and more people in urban areas and more pressure to urban areas, and the green infrastructure have been identified as one of the most important elements in order to meet these changes and new demands for urban environments. And when you look at the green infrastructure, it goes from everything from the cut lawn to shrubbery to pocket woodlands, street trees, green roof, green walls, even the pots on a balcony. All this together is recognized as a green infrastructure. But when you look at the plants, which individual plants and plantation that they have the biggest impact, trees is outstanding when it comes to delivering different kind of services and function. And we talk about this ecosystem services that trees can be delivering from urban environments in order to create resilience and so on. And this is just a compilation by Johanna in her thesis, and I just stole it. It's easier to steal stuff. That's how we do. So I just stole it. But it shows really good what trees and the green infrastructure can deliver. And the most things that you hear about is this regulating ecosystem service like stormwater management, microclimate mitigation, pollution relief, and so on. But there are also others function like cultural provision supporting ecosystem services as well, where trees can and have the capacity to deliver a great share of all this together. Because when we come to urban environments today, the spaces where it's allowed for a tree planting or plantation is get fewer and fewer. So the few places where you're allowed to plant trees, this plantation is not only to be a good-looking space to create a local identity for the place, it's equally important to serve many kind of function. So that's why tree selection is really, really crucial when it comes to create a resilient in urban environment. However, and also this, that the capacity for the trees to deliver a function increase by space and condition. So well-growing trees, large trees, of course, deliver or have the higher capacity to deliver this function. So therefore, the thing we plant here have to reach to this in order to create this resilience and so on. So what we are doing, the plant selection is really, really important. And that includes, of course, site preparation by good in plant environment, but also the plant selection. That's why we focus on this speaks anyway. And this is actually how it looks many times. This is actually a plant. This is a parking space in the southern Sweden. It looks worse than it is actually. This is a space where water can go through, and it's a structural soil here. So the main idea here was that this plantation should mitigate the urban heat island effect by shading the space, but also shading the cars, so the dogs and people in the cars don't die directly. It takes some time. But also the space is part of the local stormwater management in order to mitigate that as well. So it is good, but what the problem is here is completely wrong plant material they're selecting. They're selecting a sycamore maple, a maple tree, that needs moist condition more or less all throughout the season. And even if this is a good space, the situation will not give that. So the plant selection is completely wrong here. So you completely fail, and it costs a lot of money with doing that. And this is not a situation in southern Sweden. You can see it both there in Ithaca, New York City, all over the world, where plant selection is completely wrong for site. And we have to, because it costs a lot of money to replace this, and also producing trees are going to die and so on. So it's just stupid. So we have to increase our knowledge about plant selection. So that's one side of the coin when it comes to plant selection. The other one is this. There is a lack of diversity within urban areas. This is a study we did a couple of years ago in Scandinavia when we evaluated the urban tree population in Denmark, Finland, Norway and Sweden. And this is the street environment in Helsinki, you know this, capital of Finland, Oslo, capital of Norway. And you can see it's just few species that stand for the dominance. And if a disease hits one of these, Oslo risk to lose 44.3% of the street tree in just over a year maybe. And then you lose the resilience for that, and it takes many, many years in order to build that up again. And this is not a Scandinavian problem only. This is an international problem. This is from a study we are working on where we try to evaluate the tree diversity in urban areas around the world, in the northern hemisphere. And this is street environments as well. You see Pittsburgh, 4 species stand for more than half of the population. Beijing, China, 3 species. Camden, which is a borough in central London, UK, 4 species. Spain, 3 species stand for. So this is a situation we have around the world where there is a lack of diversity. And you can't say lack of diversity and resilience in the same sentence. It's not possible. It's not going. So what we're standing in front of, the 2 main challenges we're standing in front of is first, increased knowledge about untraditional or rare tree species in order to introduce a wider diversity of urban trees. But secondly, start to understand or start to develop knowledge about their capacity, this new untraditional plant materials, in order to grow on really challenging growing conditions, but also their capacity to deliver different kind of ecosystem services. So these are the 2 challenges we stand in front of today, and the work we are doing, they have done for many years, but we're doing here in Cornell, and we're probably going to continue forever and ever anyway. So this is just an introduction of what I like to talk about. So developing site-related knowledge. This is what Nina said, learning from nature. Because in nature, trees and plants generally had developed different kind of traits and strategies or even personalities in order to compete for resources, in order to compete for or tolerate different kind of climates and growing conditions. So by developing knowledge about which kind of traits species have, it's easy to find their use potential also in urban environments. So this is not rocket science, pretty common sense. Because in nature, there is plants like this. Plants that can take more or less everything. They have a lot of different kind of superpower. Plants that can take a punch or 2 and still be standing. I have a quote here I really like. This is Mike Tyson. Everybody has a plan until they get punched in the face. And this is really good because this is what it's all about. Some have a plan how to take this punch and still be good looking, still be standing, still be performing well. But there are plants that don't have any. Sorry?
In the case of Mike Tyson, or until they get bitten in the ear.
Exactly. And then there are plants which are stupid or maybe not that clever, that have developed less different and can't take many punches, even if this person probably deserves many punches in the face. Anyway, when it comes to plant selection, it's important to start to know how well they can take or which kind of superpowers or personality plants have, which kind of strategies or traits they have, but also how well developed these different traits are. And in urban environment, there is a lot of stress factors that affect the trees. And one of the main stress factors that trees is facing today, will probably face even more in the future climate, is lack of water. So water stress is the main contributor for trees in urban environments, because the urban environment is a more warmer climate with a more effective evapotranspiration, but also you have a very effective water runoff with all these hard surfaces. But also the space for many trees, especially below ground, is limited because of space of pipes and other things in this multifunctional place as urban environments represent today. So what we're focusing is drought stress for trees and see what kind of superpowers they have in order to deal with water. And this is a a compilation by our colleagues, Andrew Irons from my school college, that did this for a couple of years back, where he tried to put together how trees dealing with water stress. And you can see that you can divide them in two groups: avoiding water stress, and the second is just take the water stress and tolerate it. And I will start with avoidance, the tree, how trees can avoid water stress. And then you can have two subcategories, like maximizing water, this is a hard word for me, acquisition, is that good?
Acquisition, yeah.
Can you say it?
Acquisition.
There you go, I can't say it. And that's, of course, that's the main thing, is to invest in a root system that can support the tree with water. That's the main avoiding strategy that most of the plants do. Some are better, some are weaker. But then we have this one, reduce water use or reduce water loss by, for example, stomata closure, reduce leaf and stem growth, investing in pubescence of leaf, thicker cuticula, but also this one, which is less attractive, so to say, just throwing the leaves. This is a picture from close to our summer house in southern Sweden, in a place where you have a thin soil layer, we have rocks and just half a meter soil. After a couple of weeks, really warm and dry weather, the root system can't support the tree with water anymore. And some trees don't have any second plan or plan B, they just rely on tree roots. When the tree roots fail, they have no idea how to deal with the situation. So they go into panic, and you can see what's happening, just throwing the leaves in order to reduce the water loss. It's a very effective way. You can see it on many species. This is the birches, Betula pendula in Sweden. But you can also see it like this. This is from the plantation here at Cornell. Even if you have a structured soil here, which is better than normal, it's better than it looked like. These trees, this is from August 4 years ago. When they're panicking, they just have no idea what to do. The root calls the tree crown, we don't have any water down here. So they go into panic and don't want to lose anything and throw the leaves. You can compare to the trees here, planted at the same time, and they have more or less an unlimited rooting space, and they're still green and doing well. So this is an example of avoidance strategy, avoiding when it comes to roots. But there's other example of avoidance strategies. For example, this. I think I showed you this last year when I had to speak. This is silver lime, silver linden. All these American names of trees. I'm very sorry about that. Tilia tomentosa. This is a picture from Moldavia, Republic of Moldavia. But they also invest in a root system, of course, in order to avoid. But they also invest in other tools. For example, pubescent leaves. And they invest in a special pubescent or hair type, which is this star hair, which is like small micro umbrellas, which cover the, can you say underside of the leaf? Or is that okay? Thank you. The underside, sorry about it, underside of the leaf, which reduce the loss of water. So that's another avoidance strategy the silver linden use. And the silver linden have another level of avoidance strategy. This is an interesting forest just on the border between Romania and Republic of Moldavia. You have to bring your passport when you go into this forest because you never know which country you're going to end in. I've done that mistake a couple of times. But here you can say the silver linden in an oak forest. And this is a very warm and dry day. And you can see also in the plantation here that a warm day, the silver linden is more silver compared to a moist and cool day. Because on a warm day, they turn the leaf upside to the sky. And by doing that, they reflect away some of the sunlight, which makes the leaf doesn't heat up in the same amount as normal. And if the leaf doesn't warm up that much, they don't have to use a lot of water to cool down the leaf. There's a very clever way to, in a warm day, reduce water loss by reflecting away the sunlight and doesn't get that upheated, so to say. So that's some example of avoiding strategy that trees have in order. So that's what part of the research we do, and try to identify all these types of strategies, avoidance strategies trees have, and also try to understand how good they are. Root system, of course, is good, but when the root system or in the soil dries up, what kind of other plants do you have? in order to step up and take the drought, so to say. But the thing is, same picture again. Same situation, very dry, but there are trees that have the same lack of water in the soil. The root system failed to support the tree, but the tree doing well anyway. So this is an interesting strategy we are looking at, or we have been looking a little bit extra to, this tolerance that's taking the punch, so to say, and still be standing well and looking good, to take the drought in order to avoid it, so to say. Because when it comes to tolerance of water or limited water availability, there are several different kind of strategies that trees have developed. Osmotic adjustment, for example, elastic adjustment, but also low turgor loss point, which have been a special interest for us. Because that, if you have a very low turgor loss point, you have the potential to just shut up, just to stand there, take the punches, and wait out the drought. And then when the rain weather comes, it just goes on, business as usual. So that's the interesting to see how much you can shut up and how long you can do it. So that's why 3 years ago we started a project together, which is a collaboration between the Swedish Horticulture University, Cornell with Nina, but also with Myerscough College in UK with Dr. Andrew Irons. And we called the project Shut the Hell Up or Die, which actually what it's all about. Try to see how much a tree can, or why they can standing there and just shut the hell up, but also see how long you can take it, how many punches you can take, because that's important to see in situation where you need to have trees that can standing and taking the punch after punch and still looking good and deliver different. So low turgor loss points, we thought that was interesting to look at. And turgor loss point can be used as a universal measure of physiological drought tolerance that is quantified and measurable. And this is very attractive for me, rank species in terms of their physiological drought tolerance. Because today when you review literature, it's tolerant for drought. Yeah, but how much drought? That's the problem. We can't say this is better than other ones. And that's very attractive that if it's possible to rank species, actually give a number, to actually say this is drought tolerant this much and this is actually this much. Then it's easier to pinpoint which species that can be used on that site, because in that site you have to take the drought this much and so on. But the problem before is that taking to measuring the turgor loss point is a very complicated and time-consuming. Thank you. Can you read minds? It's good. Time-consuming work, which means that maybe for a year you work with 4 or 5 species, and you can take the turgor loss point for them, and that's it. But when it comes to diversity, we have to look at a large share of species in order to see the potential of which one can be introduced or for nurseries or landscape architects or tree planners and so on. But the last 3 years or 4 years ago, a group in China, together with people in California, come up with that there is a close relationship between osmotic adjustment and turgor loss point. And that makes it possible in a much easier way to develop or to take out the turgor loss point. We can use another methodology, but also it's possible with new techniques to use it more easy. So that makes it possible to take to create turgor loss point in a much easier way and faster way. So last year we spent more or less a whole year to just adjusting this methodology, testing back and forward, because the work that had been done before have been developed for subtropical, tropical, and Mediterranean plant species. And we are not there. We are working in temperate zones. So that's why we're testing back and forward. So the result last year have been actually published or accepted for publication. So it's going to be published anytime here. And we was looking at maples, 27 different species and genotype of maples we tested last year when it comes to turgor loss points. And this is what's, I thought it was interesting to actually do some kind of ranking, but also you can see, because the more negative pressure you can take, the longer you can shut up. longer you can take the drought after the root system, all these avoidance strategies fail, then you can take a longer drought before. Because turgor loss point, if I should explain it, is that when the root system fail to deliver water, you go into a wilting position. So the cell structure in leaves just shrinking. And they can shrink to a special level, and then they just implodes. And then the cell structure just gone. The investment the trees have done for that leaf, everything is gone. They can't produce any photosynthesis anymore. But this level before the cell structure just implode and destroyed, different between different species. So some species can take just 3 or 4 days of drought, and then the cell structure just goes out. But some, they have a very strong cell walls and so on, so they can take a long cells, very low negative pressure without get damaged. So this is what it is. So these species down here with a long can take, their cell structure can take a long drought and a very high negative pressure. And by doing that, they can take the drought and still have an active photosynthesis, and still can capture resources and invest in roots and shots and things for next year. And that's a very positive thing. But the species up in the top there can take it very short, and then the leaf structure destroyed. Is that, you understand, or? Pretty clear, okay. The interesting here that there is a difference between the season. You can see in the spring, some of the species that are very, very strong in the summer are weak in the spring. And that's interesting when it comes to climate change, when we have drought in different parts of the season that we never thought before. But I will go through and show it. So what it means more practically is that the trees or the species or the genotypes that belongs to the group up there, which have a very low negative pressure on the cell structure. These are the species that rely very much on the root system or avoiding strategies. So they should never ever be planted outside very generous park environments where there are unlimited resources for the roots, but also have a good water holding capacity in the soil. But when you look at the trees where they grow naturally, it makes sense. Because Acer spicatum, which was the weakest one in this test, this is the place where you can find it, along streams, as an understory species in moist woodlands. And that's the case also for Acer pennsylvanicum. I have no idea what these species calls in English. I just stick to the scientific names. This is from the Tree Man State Park outside Ithaca. But also Acer truncatum, or mono, whatever you want to call it. This is from the Qingling Mountain in China, where I did my PhD work, a lot of field work. But here you can see it as an understory tree inside a protected moist forest environment. So it makes sense. The trees that have a low turgor loss point, they grow naturally in sites. But it's a good guidance also for tree planners, landscape architects, that these trees don't have the equipment to grow in street environments where you have periods with really severe drought. They should always be a garden or park tree. That's it. But then they had the other group here. These are the guys that can take drought for a longer time. They can be planted in more challenging growing conditions like this, in a courtyard where deep rooting strategy is not that clever, because you can't force the root system through the office here, through the parking lots and so on. It's not possible. So trees here have to have a B, C, and a D plan to take this. And these guys have the potential to be growing here, be growing well, looking good, delivering all these ecosystem services they wanted in there, even if the condition is really, really challenging. And the same thing, when you look at where they grow in nature, you can find them growing in a really challenging growing situation. This is Acer grandidentatum from Utah in Zion National Park. And if you have to grow here, you have to have strategies more than just the root system and rely on that. You have to step up and take the other one. And this is from the steppe forest of Eastern Europe, Acer tataricum together with Quercus pubescens. Because if you should grow here on the steppes of Eastern Europe, you have to have a tolerance to take weeks of drought, really severe drought. And every time I have Anina in an audience, I have to show this picture. because everybody who takes Nina's classes, they know that Arcitectaricum is named as shit on a stick, because Nina doesn't like this tree. So that's why I just showing her how good looking tree it is. This is from Lund, Sweden, on a courtyard with a parking deck below. Have you seen enough, Nina? Yeah, we'll give her a few seconds there. But also in the same study, you can show that it shows that also within the same species, there is a significant difference between different genotypes. And this is interesting when it comes to selection, that within species, you can find both sensitive but also really, really tolerant genotype or ecotype within the species. This is our red maple, 3 different kind of genotypes, but also it's really attractive when my new job, when I have to travel around the world to collect species, that this methodology makes it possible to screen in an early stage the potential of the species. So if we are hunting for drought-tolerant tree species or species or the genotype for a future climate, we can use this technology or the methodology we develop in order to screen in an early stage. We don't have to wait 3 generations of gardeners before we know it's tolerant or it's weak. We can do a really early screening. So this is the work we did last year. So this year we went all in to screen as many species that we could in order to see, especially among the untraditional. So this is the work from this year. And I will go through them all. No, I won't. But this is what's happening when you get carried away in your research. You feel like an alcoholic. Like, one more glass. This is like one more species, just one more day. And this is the result here. So this is about 140 species of genotype we're testing this year in order to see. But then you can see the significant difference between species and genotype when it comes to drought tolerance. And the main work is not only to create this data set, but also testing untraditional or rare tree species. Because we can't just go to conference and say that everybody are idiots, the nursery industry or the landscape architecture industry. We have to give them some kind of guidance or confidence in order to shift from a traditional plant materials to testing new plants and new species and so on. And by this research, it's possible to actually show them that, for example, Ecomia ulmoides, I think it's Chinese rubber tree. That's the English name. I'll look it up.
Hardy.
Sorry?
Hardy rubber tree.
Hardy? No, okay. I was wrong there. Anyway, rubber tree, and you can show them that the most common tree, for example, in Sweden is Tilia cordata, and you can show that this is fully hard in Sweden, but much, much more tolerant for dry conditions. So should be better in urban street environments compared to Tilia cordata, which, when it comes to a dry condition, they have all these things going on, and honeydews and so on. But it's the same thing. It's important to identify the trees that belongs up there. Because in Sweden, anyway, the landscape architect really, really like Magnolia cobus. These are new trendy trees. They want it everywhere. And they also start to force them into street environments. But the result, they look like crap, because they just have wilting leaf in July, no flowering, die off in the tree crown and so on. So it's really important also that show that Magnolia cobus is and will be an exclusive park tree or garden tree, should never be forced. And through this research, it's possible to have that kind of communication that they don't have that. They can't take many punches. They take one and then down. So it's equally important to identify the tough ones, but also the weak ones in the communication when it comes to diversification of urban environments and so on. And through this data set, I just narrow it down a little bit to go through some plants or some groups. This is the oaks. We've done 22 different genotypes of oaks we're testing. So you can see it's a huge differences between them, also within the season. Bear in mind that this axle is changing a little bit in number. But also this work, this is from birches. This is made not here in Cornell. This is made in Ness Garden, which is the botanic garden in Liverpool, UK, by Andrew Irons. Because the man director there is just wrote a monograph on birches, so he wanted us to come there. Next year we have been invited to Kew Garden in London to do a screening of their trees there, because they want to know the future potential of the tree stock they have at the Botanic Garden and so on. So the word started to spread there. So I hope next year we can present some really interesting data when it comes to rare trees from Botanic Gardens. But also we try some shrub species, me and Nina. You can also see this is ground covering shrubs we just started with and play a little bit with. But then you can see also there is a big difference between species and cultivars, but also when it comes to use potential, where the potential is. So this is what was my goal when we started this, because I will try to explain this. Pretty boring, I know, but I'll try to explain it. Nina Metz and Valadares presented a paper 2006 by ranking drought tolerance for 800 wooded species, shrubs and trees, by reviewing where and how they grow in the wild. But this is once again just assumptions, like between 3 and 4, so it should be a little bit drought tolerance. But what we can show, we put our data based on their ranking, and you can see there is a relationship, really close relationship with our data with them. But what we can do, we can actually show not only like between 3 or 4 should be there, we can actually show a number. This is how it is. But it's also interesting that some of our most drought tolerant species, for example, Syringa reticulata, what's the name of that?
Japanese tree lighter.
There you go. Japanese tree lighter. Which is drought tolerant. But when you base things on review or review literature, you can read about the species where it grows in southeast Siberia, when it grows in cool and moist sites. But when you go to the mountains in China, it grows together with Ailanthus or Coroteria, one of the most drought-tolerant species, on very, very rocky and dry sites. But that book they didn't read, so that's why they put them in as not that drought-tolerant. So that's when you're reviewing ecological literature together with the research we're doing. So as I said, we are in a start, and we start to develop this database. Hopefully next year we can add another 100 to this list and so on and work it on. And we have a lot of side projects, which is interesting, where you can see that if you stress a tree, they can step it up and actually increase the turgor loss point and so on. So also important to see the window, how much they can take, not only when they're growing in park environment, but also when you stress them and see how much they can step up. Some species doesn't have that capacity. Some species have a very wide capacity. So bear in mind, this is just the starting. But I think it's really interesting, and most of all, it's really interesting or very useful in order to communicate with tree users, plant users, and plant designers. How much time do I have left? Okay. Then I would like to show another perspective that we work with as well. Because when it comes to plant selection, many things that trees, right tree for right site. But I would like to add another aspect of that, right tree for right site and functions. Because when it comes to urban tree or urban forest today, everybody's talking about increase the urban tree canopy and so on. If we increase with 10%, we will gain this, and if we add another 10%, we will gain this. That's not possible. I can't buy that, I'm sorry. Because it's different between trees and trees. Because when it comes to landscape architect, and I'm one of the most hated teachers in my university, because I'm the guy that shows up in the presentation and just asks them, why this green blob there? What is it, and what should it do there? I don't know. It's a street. We plant trees along the street. And then I fail them. They have to come back. They have to, every dot, they have to have an idea why and which tree should be there. Because when it comes to buying a car, we don't go in and say, I just want to buy a car. We don't do that. Because when we buy a car, we have a lot of ideas what we want for the car. What kind of car? How should I look in the car and so on? What kind of stereo? What kind of all this bling bling? But if you don't do that, if you just go in there and say, I want a car, you can end up with this one. But that is good. That's a lottery. But at the same time, you can end up with this one. Both is a car, but the capacity between them is different. But this is what we're doing when it comes to tree selection for ecosystem services. Or trees are good for pollution, reducing pollution, or mitigating urban heat island. So that's why we plant tree, without thinking of where to place them and which species to use. And that's very, very frustrating, because it's much more, because this tree is not a tree. Sometimes it goes well. This is two good examples. This is from Stockholm, this is from Manchester in UK, when the tree selection have been really good. Probably it's just luck. But sometimes they're using species that doing a good job there, taking the wind or shading the situation where it's needed. But sometimes sometimes you can plant tree and make more problems rather than actually benefits for the tree. And I would like to show, this is research I'm just part of. So Johanna, raise your hand, is the main person behind this research. I'm the plant geek. I'm in the end just adding some trees and so on. But I would like to just show this. This is a program, a climate modeling program, where it's possible to see the effect of urban green infrastructure and how they can adjust the microclimate in a building area. It's like Minecraft for grown-ups. You're building up vad heter kvarter? A neighborhood in a 3D way. This is the houses, and then you add numbers of the houses. If it's a concrete house, it's a wooded house, how tall they are, what kind of roof it is. If you have climbing plants and also which kind of glasses and so on. But also, it's not only taking the build-up environment, but also the outdoor environment. What kind of surfaces is it? Is it concrete, gravel, grass? Is it shrub plantation? Is it a tree? How tall the trees are? Which kind of levels and so on. And then you build this up. It's called MVMet, and then you can download it for free on the internet. And then you add local climate data. And then you press the button and take a weekend or 10 days or so. And then you come back, and this have been harvesting for a long time. But the problem in the beginning was that the plant data is not available. So the work we have done for 3 or 4 or 5 years. Yeah.
There is context, there is default context, but it's based on tree variability.
Yeah.
And they were very, very high. They sort of resemble energy variability like in the forest. Very, very dark.
Yeah. Yeah.
So when we look at the cities, trees restricted in urban environments in Scandinavia, we find that tree variability data that we have to have.
Yes. So we have been collecting this leaf area index data for, I think it's about 75 or 80 tree species. And then we add these values in. This is what we can have. And then you can ask different kind of questions. It's also for pollution, but also for wind speed, from microclimates and so on. But then you can get a good pictures. And it's not only you here in the USA that have stupid politics like Donald Trump and so on. Also in Sweden, we have pretty slow-minded people that are politics. But this is a model where it's possible to show or to communicate the effect of green infrastructure within building areas. I will show you when it comes to wind speed. This is the housing area with no trees whatsoever. This is the ocean here. There's a lot of wind comes in. So you can see there's a really window, especially in this passage, when you force the wind in, and here you have more or less a storm every day. And it's really good when you do this study to ask dog people, because people with dogs need to go out every day, even if it's snowstorm or raining. So they know, you can ask them, where's the worst spot? And then can actually give the exact same what this modeling program do. But this is the effect if you add due to the master plan, what a fancy landscape architect company in Stockholm did. I don't think they even were here to look at the site. So they did more a traditional way of placing the green infrastructure, trees here, group of plantation here and so on. So you can see that they reduce the wind something. But what we did after that is to place, just to change some of the species to other species, but also place them in other sites, so to say, in order to gain most effect. And this is one proposal, and this is the one. So by using this program, but also adding, you can show that species selection, not only placing the species, but also which kind of species we're using, matters. I think it's cool. And this is on the summer. But when it comes to winter, you have the branch area index. Because we have long winters in Sweden, we need to care about how the trees are acting in the winters. Because in the winter, we don't want any tree, not close to buildings, because the sun that hits the buildings in wintertime warms up as much as we can reduce 30% of the heating cost. That's a lot of money we can use by just using the sun energy, just hitting the facades in the wintertime. So by placing trees too close in the wintertime with too dense canopy, it can cool down and actually increase the heating costs in the wintertime. And then we have a negative ecosystem services actually. That's bad. So by placing trees, just increasing tree canopy without actually thinking about where and how to place them, we can actually cause problem. So this is what we want. We want trees that have a dense canopy summertime with a lot of high leaf area index that cool down facades and building, or even if we have a square where we have torghandel, markets or so on a square in the summertime. We want to have shade. But in the winter, we want to have a lot of sun. So what we look at is trees that are dense in the summer, but sparse in the winter, and let a lot of sunlight through the tree canopy. So we did a research of evaluating different tree species when it comes to branch area index. And this is Ginkgo biloba, which is more like a joke when it comes to shading wintertime, because it doesn't have anything, more or less. But then we have this. This is a Carpinus betulus fastigiata, which is a hornbeam, upright, which is very, very dense. So this can shade a lot. But at the same time, the ginkgo can't reduce any winds in the wintertime, because winds is another chilling factor. So you don't want to maybe have trees close to the buildings, but a little bit further away to reduce winds. So ginkgo doesn't do anything, while the hornbeam do a great job for that. And then we have something in between. This is Islandus. So we did an evaluation about 55 or 60 species or genotypes of trees, about 35 years old, planted at the same time, planting the same site and so on. So it was evaluating. So you can see that when it comes to branch area index, that's the density of tree crowns in the winter. You have ginkgo. This is from Stockholm, a new ginkgo plantation. But one of the most dense is the upright Carpinus, or the hornbeam. So what we did, we are playing around with this EnviMet again. And then we place, this is a courtyard, this is a buildings, the main wind comes from the west here. And then we placed a tree row. It looked like it's a hedge, but it's not, because in the program, if the canopy touches each other, then it looks like a hedge, but it's not. It's just a traditional tree row. But what we did is using the data, or the values we collected from this, the data, the field, the branch area index data, and added into the program to see how much they can reduce the wind, which is a very important ecosystem service when it comes to Sweden in a way, because we don't have that warm summers, but we have cold winters. So reducing the wind and the cold temperature wintertime is more important in order to reduce energy costs, but also a really good outdoor environment. So we go through. This is Ginkgo biloba. This is Norway maple, emerald queen, honeylong locust, or Gleditsia, turkey oak, Corylus coluna, Fastigiata hornbeam, and last upright type of western pine. But then you can see so we have to care which trees we are placing where, because there is different capacity within between species and even between genotype within the same species. So we can't just say that if we increase the tree canopy with 10 or 50%, we will gain that and this and so on. We have to be more precise. We have to force ourselves in the planning of the green infrastructure to talk about detail, to talk about plant selection, but also the spacing, where to put them and so on. And this is really clear research that really shows. And this paper is out. It's published early this year. So if you want some copy of this paper, please let me know. I will send it to you. So to summarize this presentation is that I would like to launch the statement that the cool people, the most important people, the new superheroes in the future will be the plant geeks. Because the plant geeks are the people that knows all these stupid facts about plants. But these stupid facts, all these details are important in order to build or construct resilient urban environments. So that's it. Thank you very much for listening.
Looking at the graph that you showed with the drought tolerance for spring and then for summer, you're concentrating on the summer data and more or less ignoring the spring data.
No, actually, maybe in my talk here, but in the presentation we care about the spring data is equal, because it's interesting that the weak ones, so to say, they have more or less the same values in the spring as in the summer. They don't change that much. They go out weak and stay weak. But interesting that the most drought-tolerant species in the summer, some of them are really, really weak in the spring. For example, the golden rain tree, Horticulture Section, it's one of the weakest in the spring. But in the summer, it's maybe number 1, number 2 in our data so far. It's really, really strong. And that's also important when we transplant the trees or establish the tree. They are very weak in the beginning, so we have to focus, even if it's drought tolerant when it's established, it could be really fragile in the establishment phase, especially in the spring phase, that we have to be really careful to watering the plants and so on.
But is what's happening then with this adjustment from the spring to the summer, that you're having osmotic adjustment by the tree because you've got a series of small stresses during that period, which adapts it to the drier conditions?
Exactly. So that's also the next step. We have some spin-off studies going on beside this, trying to compile this big data set that we have trees that grows, for example, in the plantation, we have unlimited, the same species or even the same genotype downtown with more restricted planting. We have been actually done some root penetrating routers. We know exactly how much space they have. And then you can see that the trees in the plantation, of course, because if I have unlimited, why invest that much? Because everything's good here. The downtown, they invest very, very much higher. But interesting in this data that the Horticulture, the golden rain tree, have the same high levels even in the plantation as downtown. So they just invest in very high or very low turbulence point, even if they are standing with unlimited rooting space. They just program to be really strong from the beginning. They don't have any other thoughts. But for example, Quercus polybergia, which is the other species in the same study, have this huge adjustments between plantation with unlimited space compared to, for example, the library downtown, where it's very limited rooting space. They have maybe half or double its turbulence point. You can take it more because they have adjusted for the side. So what we see there is among some species just have a very strong from the very beginning. So what we can see that there's a lot of things we have to continue to look at. But what's interesting is to developing knowledge about the window, how much you can take, or the adjustment. That's the next step in this research, to try to understand which species have a very narrow window. For example, Cercidiphyllum or Asus picatum, it goes out weak, stay weak, and doesn't have any adjustment. But then you have some other species like Quercus polybergia that have a way wide window of adjustment. So that's the next phase, to try to create this window to see how wide they are and how narrow they are. So we are working on it.
Henrik, along those same lines, if you look at a moisture release curve for a soil, a sandy loam soil, the volumetric water content at a water potential of -4 megapascals, for example, is vanishingly small. Not a whole lot of water even left there. It might be interesting to look at the duration of drought in reference to something like potential evapotranspiration, to see, so to speak, to use a different metaphor, how long the plant was going to have to hold its breath. If you're investing a lot of energy in making neutral osmotica for osmotic adjustment, and you're going to get another 6 hours worth of ability to extract water, that might be a less prudent kind of adjustment or investment.
Yeah, definitely. I totally agree. The thing through this methodology we develop, we come up with new spin-off and try to relate it here, try to relate it there, and so on. So yeah, I totally agree. We should look at that as well. So we are in the very beginning of this work. So by creating this data set, and next year we're going to work with 3 places: Kew, Gothenburg Botanic Garden, but also continue here in Cornell. So while we create this database, it's a great chance to start to play with it, to try to see the same thing but from different angles and start to play with it. I totally agree with you.
Okay, I think we're out of time.
I would like to end by say thank you for having me here for almost 2 years, and I would like to thank Nina, of course, for taking so good care of me here, both in Cornell but also outside the work here, by helping me to get a credit card, American credit card. No idea how I have a social security number. That's impossible. We did it. We had to beat up some people. But also the people at the department. I really enjoy to be here. And we have some, as you probably understand, we have a lot of things going on, and I will come back here. But I want to thank you for this time. I really enjoyed it, and it was really inspiring to be here. So thank you very much.
This has been a production of Cornell University, on the web at cornell.edu.